Here we have more pairs of molecules, and we're going to decide what is the relationship, stereochemistry wise, so stereochemical relationship. They can be the same, so identical molecules. They can be constitutional, enantiomers, or diastereomers. So let's see what is the relationship between this. Let's go ahead and analyze the first one. In the first one, it will seem like we have an inversion here and an inversion there. So that is inverted, that configuration. And the other center is also inverted. But that's a special case of a molecule. This compound has a plane of symmetry. So even though they look like, because of the two centers being inverted, they look like an enantiomer, but it turns out they are the same. When you have an internal plane of symmetry, we will call this a meso compound. And it's actually this molecule the same as that. We're going to prove it. Say that you have this molecule, and now I'm going to do 180 rotation. When I do that, remember that we said that what is in the right is going to go to the left. But what you have in wedge pointing towards you is going to switch places what you have in the dash. So here you have the hydrogen in wedge, in chlorine in dash. Same here. So when you do the 180, you're going to get that. So they are identical. So when you have two mirror images, these, and they are superimposable, this actually is the enantiomer if you see each chiral center. But actually, when you do this operation, they superpose exactly with that. So it is the same molecule, and it is because you have an internal plane of symmetry. That is a meso compound. Okay, let's go to the molecule that we have here in below. So check out one chiral center here. This one has an OH. So I'm going to do a little circle here. This center is also chiral. Remember that you will recognize that it has 4 different substituents. So here, this one has OH, an H that is not pictured, and then the chain traveling this way is different to that. So that's a chiral center. The second dot, you will have an H pointing towards you in a wedge, and then this chain is different to that, to that. So that's another chiral center, and you have a third chiral center that has an OH, an H that is on dash, and then the metal and that, they are different, so 4 different substituents. Now, same here, 3 chiral centers, and we have the same connectivity. So OH, OH, and that group is the same, and OH here. All right, so what are this related as? We remember that this is a picture of the mirror images of a compound. They're not superimposable. So these two are enantiomers. You can picture the enantiomer like that or like this, meaning that if when you have multiple chiral centers, if every center is inverted, then that's the enantiomer. That was like that, but it turns out the enantiomer superposes with the original molecules because that was an internal plane of symmetry. But let's see what happened with the configuration of each chiral center in this molecule. Here, the center OH on dash, OH on OH. That center is inverted. That center here on the where this group is, this is on dash, this is on OH. So it is one inversion. Inverted, inverted. Let's check out the last center. Not inverted, same. So if you have 2 are inverted, or not every center is inverted, these 2 are diastereomers. All right, so we can also do the absolute confusion and check that out. Here is easy. So OH is your highest priority. Then your second highest, I'm going to do 1 is here. Then 2 and 3, the hydrogen is in the dash. So I'm good. This is R. The second center here is, you're going to see priority 1 is this here because you have an OH. So priority 1, priority 2, priority 3. Oh no, did I do that right? Yeah. Priority 2, priority 3. So if you have a question about how to do priorities, I have videos on that. But the thing is that sometimes you need to break the tie. This carbon, the H is in the dash, so we're good. But here you have the carbon analyzing the center. This carbon is attached to an oxygen, to a carbon, and to an H. The other carbon on the right hand side, this carbon is attached to a carbon and H and H. That's a CH2. Same here, carbon HH. Though you need to break the tie, you move on one more position, and then you're analyzing this and that. This carbon is attached to an oxygen, to a carbon, and to an H. This carbon is attached to another carbon here, into 2 H's. So clearly, that's your priority 1. So we do 1, 2, 3. That's R. And last center is priority 1 is the O, then the chain on the right. So I'm going to do 1, 2, and 3. Turns out is R. Okay. And now that I have that, let's see what is the configuration of the other center. That's easy. That's the same. Right? Here you have one switch, so the configuration is inverted. And here the configuration is inverted. So 2 of the centers, so RR. This is RR inverted, but this one is the same. They are diastereomers. Okay, now let's look at these chairs right here. The compound here is, we're going to name it, it is 1,2-dimethyl cyclohexane. So I'm going to write it down small to make room, right? Dimethyl cyclohexane. All right, it is 1, 2 because 1 and 2. Not only that, this is pointing up, this is pointing up. So this is cis 1,2-dimethyl cyclohexane. Now let's look at the other molecule. If I name this carbon 1, this is 2, this is 3. So this is 1,3-dimethyl, and then I don't have room, dimethyl cyclohexane. And pointing up, pointing down, that's trans. But what's important is that the metals here are attached 1, 2, and here is 1, 3. So these are constitutional. Constitutional, meaning connectivity is different. Same molecular formula, different connectivity. All right, let's analyze this one below. For that, name-wise, this is 1,2-dimethyl cyclohexane, just like this one. But this one has one metal pointing down and up. So this is trans 1,2-dimethyl cyclohexane. And this is actually up. So this is the cis 1,2-dimethyl cyclohexane. So this one is the same. So if you had a question having these two pictures, then these two are the same. This is pointing up, and the connectivity is 1, 2. So 1, 2, cis 1,2-dimethyl cyclohexane. This is trans. So when you have stereoisomers, cis trans, these are diastereomers. So these two are diastereomers, but these two that I have connected here with the arrow are the same molecule. Okay? And these two are constitutional. Now let's go here now, example with a Newman projection. Now this is Newman and this is line drawing. So we need to figure out whether the connectivity is the same. So now I'm going to just redraw this as using line drawing. So I have this carbon right here. I'm pointing at this. Has an ethyl and a metal, right? So I'm going to have that, yeah, like that, metal, ethyl. Then the carbon in the back. So this is the one in the front. The carbon in the back. Oh, it should have done this like straighter. The carbon in the back has a metal going down in 2 H's. So that's it. See, so again, this is this carbon. It has an ethyl, so that's why I did this too. And then it has a metal. This is this metal. This is a carbon in the back. Oh, that, which I'm gonna draw here in a different color. The carbon in the back has a metal going down into H's, which I'm not picturing. So here we see, if you want to name this, this is 1, 2, 3, 4, 5. So it is 3 methyl pentane. Pentane. And this is 1, 2, 3, 4, and 5. So this is 2 methyl pentane. So what are they? The connectivity is different, so they are constitutional. So if you have this kind of drawing, let's pass this, convert this from Newman to the line drawing. You can also do the other way around. But now we know connectivity is different, so they are constitutional. So I'm going to do now the last point here. This is easier if we make this a line structure. So now, I'm going to draw a line, say, for connecting the carbon in the front and the one in the back. I'm going to erase this one so that we have a little bit of room to do the last problem, which has 2 Newman projections. And what I'm doing is I'm going to redraw that as a line drawing. So let's do one line that is this carbon in the front and the other carbon in the back. That's that line. The carbon in the front has a metal going up. Well, you know, I'm not going to even draw the metal. Just going to draw a line. That's a metal. And I have HH, so I don't need to draw anything else for that carbon. That's the carbon in the front. Let's do a dot here. Now, the carbon in the back is this. And what does it have? It has a metal going down. See this here? But now I have chlorine is to your right-hand side. So I'm going to draw that on a wedge. Now let's see what happens in the other picture. Again, I'm going to draw a line saying that this is the bond between the carbon in the front and the carbon in the back. The carbon in the front has a metal going up. The carbon in the back, metal going down. So the skeleton is a butane. And by the way, this is 2-chlorobutane. And we can add the configuration 2-chlorobutane. This is also butane, so 1, 2, 3 is a carbon in the back, and 4. And here you will do the same. 1, 2, 3 in the back, that's 4. 1, 2, 3 in the back, 4. And this is what I'm doing. So carbon in the front has this metal going up. This is this carbon bonded to the carbon in the back, and this is your carbon 4. Now, what we see here is the carbon in the back has a chlorine on the left. So I'm going to do a dash here. So what it is, what do we see? This is still 1, 2, the naming, name-wise. This is 2-chlorobutane. So 2-chlorobutane, and but so connectivity-wise, they are the same. But this chiral center is inverted. So when you're naming it, you need to specify that. So 2-chlorobutane. And of course, if we have only one chiral center and is inverted, these two are enantiomers. Okay, and now the configuration of the chiral center is Priority 1 is the chlorine. Priority 2 is going to this chain. The hydrogen is in the back, the lowest priority in that. So that is S. And here, it will be exactly the opposite because remember we did one switch. So these two are again enantiomers. Is that how you do the analysis of the stereoisomeric relationships?